All right, we are moving on with area, so let's do a quick review at the beginning to see if you remember how to find the area of a triangle, a parallelogram, a rectangle, and a trapezoid. So see if you remember those formulas, and if you do, pause and fill them in and see how you did. Okay, so did you remember that a triangle is half of a rectangle, so therefore it's base times height divided by 2. A parallelogram, even though it looks right, like you can't find the area of it, you just calculate the base times the height. Remember, the base and height need to intersect at 90 degrees. So does the height have to be on the inside? No, I could draw it out here. But this height right here, it's on the outside of the parallelogram, but still they're the same value, right? So parallelogram is base times height. You just have to make sure you can understand what the height is in the parallelogram. A rectangle is base times height, and a trapezoid is 1/2 height times base 1 plus base 2. Or sometimes people like to write it like this, base 1 plus base 2 divided by 2. These two things multiplied together divided by 2. So you can put the 1/2 in front, same up here, you can put the 1/2 in front, or you just multiply together, divide by 2, multiply together, divide by 2. So now we are going to learn how to find the area of a 5-sided figure or a 6-sided figure or some kind of regular polygon. So far we've only done quadrilaterals and triangles. Now how would I find the area of this regular hexagon? Remember, what does the word regular mean? It means that every single angle has the same measure and that every side length has the same measure. So if I'm drawing an altitude here from the center out to this edge, or something that's 90 degrees, then I am splitting AB in half when I do that. So this becomes 5 and this becomes 5. How do I know that? Because right here it says that AB is a length of 10. So I need to find the length of OH. Okay, so how would I find the length of OH? Well, I've created this. If it's a regular hexagon, then I have 6 triangles going all the way around, right? 6 triangles. If I didn't split it in half, this would be 1, 2, 3, 4, 5, 6. This one being right here to begin with. Now, we also know that the degrees going all the way around the circle is 360 degrees. So when I divide that by 6, I get every single one of these angles in here is a 60-degree angle. Well, then I split it in half to make this 30 degrees. So what I end up having here is a 30, 60, 90-degree triangle. So if this length right here is 5, that meant that this length here was 10. So now I'm left with one piece of the triangle where this is 5, right? This is the letter A, the letter H, and this is the center O. This is now 10 because we said this is an equilateral triangle. So AO is 10, AH is 5, HO we don't know. That's what we're trying to find out. So how would you find it out? You would either know the 30, 60, 90-degree triangle shortcut and say this is 5, the hypotenuse is 10, so the longer leg is 5√3. Or you could do the Pythagorean theorem, and you'd say that 5 squared plus x squared equals 10 squared, 25 plus x squared equals 100, therefore x squared equals 75, so x equals the square root of 75, which is 25 times 3, and the square root of 25 is 5, so that's 5√3, same. So now we know the length of OH is 23. Or sorry, 5√3, excuse me. So now we're going to calculate the area of triangle AOB. So how would we calculate the area of the triangle AOB? So this is AOB, that's just one triangle in here. So we know the length of AB is 10. We know the height is now 5√3 because we just found that out, that's OH. And how do you find the area of a triangle? Well, the area of a triangle equals base, which is 10, times height, which is 5 root 3, divided by 2. So what can I do here? 2 goes into 10 5 times. I multiply 5 times 5 root 3. That just becomes 25 root 3. And divided by 1, so we don't really do that. We just have 25 root 3 is the area of one individual triangle, right? The area of triangle AOB. So I'm doing area sub, so it's identifying what it's the area of. So remember, when you're multiplying this, the numbers on the outside stay on the outside, the number underneath the radical stays underneath the radical. So this is the area of one triangle. But this regular hexagon has how many triangles that are identical to each other? It has 6 of them. So we're going to multiply 6 times the area of the 1, right? So 6 quarters is 150. Those numbers are on the outside of the radical, so they stay on the outside. So there I have it. If I asked you to leave the answer in radical form, you would keep it like this. If I asked you to round your answer to the nearest tenth, then obviously you would multiply that out, and you would get, let me calculate it, about 259.8 units squared. So notice I didn't give units, therefore I'm not really writing them, but if I did give centimeters or inches or feet, you'd have to put that unit squared. Okay, now what makes me laugh is when you guys were taking the ALEKS assessment, some of you were asking me about an apothem. Remember apothem or apothem? And I said, oh yeah, we already learned that in first semester. I was wrong. We were learning that right now. So we did the perimeter, we did the distance around the outside edge of a polygon, and we had a formula for that. But now we're finding the area. So how can we do a shortcut to find the area of this regular hexagon out here? Well, look at what we did. We multiplied what times what? So if OH is known as the apothem, right, so that's here, this is the apothem. So we have one, well, I don't know, you try to figure it out. So you read about it, read through this and see if you can understand why this is going to work. So have a little pause, read through it, and try to figure it out. Okay, so the theorem says the area of a regular polygon is equal to half the product of the apothem and the perimeter. Okay, so let's think about that. So we got one triangle's area. So one triangle's area is base times height divided by 2. But the base was just one outside edge of the regular hexagon out here, which was 10 in that case. The height, we're now replacing that with the apothem, because that's what we're renaming that height, right? That's now called the apothem. We're dividing that by 2. Well, this formula, okay, we see the dividing by 2, we see the A, but why is the P there? Well, usually in the area of a triangle, we would just have one base. Except now, instead of having one base in this regular hexagon, we have 6 bases. So remember back here, not only did we multiply by the one base, which was 10, but we actually multiplied by 6 of them, because there's 6 of them going all the way around. So you just take the perimeter all the way around that outside edge, and that's why we have the A times the P. I'm not sure I explained that very well in this video, so if you have a question, you didn't understand that, please ask me in class so we can review it in person. Okay, moving on. So now we're going to use that formula to solve for these problems. So go ahead and take some time. Maybe you want to pause now and fill some of this out, and then unpause and we can go back through it. So first you're going to find the measure of a central angle for each figure inscribed. So you would draw the figure, right, and you're drawing the center and you're making 4 triangles in there. And if you made 4 triangles, what would this central angle be? So a regular hexagon, we just did that one above, that was 60 degrees. A regular octagon. So what does that mean? That means we have 4 triangles going around here. So we have 4 angles for the square. Sorry, I'm going back to the square, but there's 360 degrees all the way around. So each angle must be 90 degrees. So this is 360 degrees. There's 8 triangles in an octagon. So you need to take 360 divided by 8. So each angle, central angle, is 45 degrees. A dodecagon is 12-sided figure. So that's 360 divided by 12. So each central angle, again, emphasis of central angle, is 30 degrees. So one of the best things you can do is probably draw the sketch. It says here, leave the answers in radical form when possible or when necessary. It's never necessary, so I should put when possible. So if you're getting radicals because you have a 30, 60, 90 degree triangle or a 45, 45, 90 degree triangle, remember we're going back to those special case triangles. So here's a quick reminder. If this is x, this is 2x, this is x root 3, right? And my second one, my 45, 45, 90 degree triangle, these are the same. So 45, 45, 90. If this is x, and the hypotenuse is x root 2. Of course, you can always use the Pythagorean theorem if that helps. Okay, go ahead and pause, answer these 6 questions on your own, and then come back and check your work. Alright, these problems are not easy. They're a little bit time consuming, and they always go back to all the information you have learned. You have to remember the special case triangles, Pythagorean theorem, what an equilateral triangle is, square, what the rules are, properties of these shapes. So here we have it. So if you remember the shortcuts, then there's less work for you to do. But if you look at this first example, we have a regular hexagon, and the apothem is 6. So here's my 6. Well, if you forget that in a regular hexagon, you have a 30, 60, 90 degree triangle, right? So this was 60 degrees around here, therefore it split this into 30 degree triangles. So this is 60 degrees because it's equilateral. Then you have to use Pythagorean theorem, or this is x, this is twice x. And if you forget the relationship, you're going to have to use Pythagorean theorem. X squared plus 6 squared equals 2x, that quantity squared, so make sure you're squaring the 2 and the x, and then you solve. Or you would have said, okay, well 6 must equal x root 2, so I divide by root 2, right? So x equals 6 divided by root 2, but I can't have a radical in the denominator, so that makes me cancel. I get 6 root 2 over 2, but that becomes 3 root 2. Oh, sorry, that was supposed to be root 3. I did all that wrong. Great. So here you go, 6 root 3, so it's going to be 2 root 3. Phew. So x root 3, oops. Root 3, root 3, root 3, so 6 root 3 over 3, which becomes 2 root 3. Ooh, now we have the same thing. So only this little portion is 2 root 3, so I need to double it. So my base is really 4 root 3, but there's 6 bases. So now I plug into the formula 1/2 times my apothem times the base times 6, because there's 6 of them, because it's a hexagon. So you should get 72 root 3. For letter B, this one was straightforward. I gave you the length of the apothem. I said it's an octagon, which means it's an 8-sided figure. So when I gave you the side length of 5, we knew there was 8 of them, so that's why I have 5 times 8 here, because I'm getting the perimeter, which is 40. I take 1/2, 3 times 40, so I get 60. For letter C, an equilateral triangle with an apothem of 8. Now look at this funny picture. This is what it means, that remember the apothem goes from the center of that to one of the sides. It splits it in half. That side that we're intersecting in half, and it intersects at 90 degrees. So therefore, if this is equilateral, that means this was a 60-degree angle down here, so when I split it, I get a 30-degree angle here in the lower left corner, a 60-degree angle here, and this is 90 degrees. This length is 8. Well, knowing my special case triangle, if the side opposite 30 degrees is 8, this is 16, this is 8 root 3, plug into the formula, and that's it. We're running out of time. Check the rest of your answers. Ask me in class if you have questions. Okay? or I can